All right, thanks for coming. Actually, before I start, can I get a show of hands? How many of you use Spark? It's about half of you. Okay, so this talk is semi-Spark related, but not exactly. It's semi-related to Scala. It's actually the first time I'm giving this complete set of talks. I've given a subset of this before, mostly just touting how good it is, but this time I actually want to drill a little bit more into the details about how we actually did it. And it might be the last time I'm giving this talk also, because I'm pretty sure somebody else is going to set a new record this year, and possibly beating the past year's. Well, if they set a new record, they have to beat last year's record. And then it would be pretty lame if I keep talking about the past record, instead when somebody else already beat us. So enjoy the moment while you can. So today I'm going to talk to you about essentially what you probably know what I'm going to talk about. But let me introduce myself a little bit first. So my name's Reynold. I was a PhD student back in the UC Berkeley AMPLab, where Apache Spark was developed. And for the purpose of the talk, I'm not going to introduce or talk too much about Spark, assuming people know roughly what it is. If you don't, can you put up your hands? There's one. Okay, so Spark is a cluster compute framework, and we can talk more offline about it later. So on leave from my PhD, starting Databricks, and I worked fairly extensively on Spark, as well as some of the other stuff we work on at Databricks. So for a lot of you that have seen earlier presentations of Spark, you've probably seen some slides like this that says Spark is fairly fast, it is in memory, and when you run sort of iterative algorithms that repeatedly scan memory, it can be up to like 100 times faster, sometimes even more than 100 times faster than Hadoop. And as a result, we have also started, as Spark was growing more and more popular, there's a lot of misunderstandings that's being developed. How many of you have heard some variants about this in the past? A few people not, and yeah, so there's some, and the number of people that put up their hands are sort of getting less and less as every talk we give, so that was good. So the two biggest misconceptions about Spark, especially for new people coming to it, is that they thought Spark is a memory framework, so you can only use Spark to process data that actually fit in memory, which is actually pretty bad for big data, because often you might have data that doesn't fit in memory, simply. And then, or more often than not, maybe you just don't want to spend as much money to buy a cluster that can fit all the data in memory. And so really, the goal of Spark is it's not really only about memory computing. We want Spark to be the single platform that can process from smaller data, medium-sized data, to very large-scale data processing. And this effectively means you could go being able to process gigabytes, terabytes, or even petabytes of data. Now, the first time I gave this talk in New York, actually somebody asked me, what about kilobytes? So I've since revised my slides to actually include kilobytes also. And Spark should really work well sort of across different storage medias regardless of memory, solid state drives, or disk. And it should also work well from very low latency streaming jobs all the way to very long running batch jobs. So for example, in Spark streaming, each micro batch job might be running in the range of hundreds of milliseconds, whereas in the case of very large scale batch jobs, longest one I know of actually runs for over a week to process feature extraction over petabytes of data. And then now, that leads me to the short benchmark. When we were when we first started Databricks, we understood there was a lot of problems with Spark in terms of scalability, which hasn't been battle tested as much as like Hadoop MapReduce and all the other more mature systems back then. So we spent a lot of effort actually trying to tune Spark, rewriting certain components of it to make sure it would perform very well under stress. And then we needed sort of a way to test this, and then we were looking to the internet, and we found this thing called a short benchmark, which is actually proposed by Jim Gray back in the 80s. So Jim Gray is a Turing Award winner, one of the guys I respect the most. Unfortunately passed away or disappeared from the sea back in the 2007. So he proposed this short benchmark, and the goal is very simple. Given some amount of data, sort it as fast as possible, regardless what you use. So you can even build your custom FPGA chips or even ASIC chips to actually store these data sets. Initially, it was actually a fairly small data set. I think it was supposed to store a megabyte or something back in the 80s. And over time, it's grown to actually 100 terabyte range. And then there's a lot of companies and sort of academic institutions that actually participate in this benchmark. Usually in the past, it's won exclusively by very large companies or very large research institutes that there's a lot of time to burn. So, as I said, back in the 80s when the benchmarks were first proposed, you just supposed to store a megabyte. And then over time, it's grown. Actually, in 2009, the standard right now is you have to store at least 100 terabyte. There are many different categories in the benchmark, even though you're just supposed to store 100 terabyte, there are different ways you can store them. For example, there's one category called the Daytona category, which is what we participated in. You're supposed to store 100 terabyte in a fault-tolerant way, which means if one of the node goes down, this should then affect your sorting process. And the input and output needs to be replicated. So 100 terabytes is actually about 1 trillion records. In the benchmark, they have a third party sort of harness to generate the data. And it's basically a random data generator to generate 100 byte records, 10 byte keys. So you're supposed to sort based on the 10 byte keys. Then we set a new record back in October using Spark. And of course, Spark's running on Scala, so Scala and EC2. So it actually become the very first time a open source software plus the public cloud infrastructure has won this benchmark. And we tied with the team from UCSD, University of California, San Diego. I can talk about the difference later, actually. It's fairly interesting to me, but maybe this deserves a different time. One thing I find pretty amazing is in the sort benchmark we were running, we were actually, at the end of the day, our sort program was able to saturate all the SSD. There's 8 SSDs on each of the machines on Amazon EC2. We were able to saturate the SSDs, and we were able to saturate the 10 gig network. And then, of course, it's 2014 back then. 100 terabytes is not a lot of data, so we also went ahead and actually sorted the petabytes of data just on our own without following the benchmark rules. There's no rules dictating how you should store a petabyte. So back in, you've probably already seen this from the abstract. Back in 2013, Hadoop's record was set by Yahoo. They used 2,100 machines and sorted 100 terabyte in 72 minutes. And then in 2014, we set this new record, shrinking the time to about a third of what it took on Hadoop MapReduce, and then using only about tens of machines. Given the machines are probably slightly more powerful because 2014 model versus 2013 model, but we're pretty proud of the result. And one interesting question I get quite a bit is why sorting? It seems stupid to store 100 terabytes of data. Why do you ever need to do that? And the reason is it's really not about sorting itself. It's this operation called a shuffle, which is actually the most common operation in distributed computing. What it does is essentially exchange of data between different machines. So for any realistic workload you want to run, for example, joining 2 data sets together, there's some sort of data exchange happening here. And for example, if you want to run a machine learning algorithm, you might actually send different messages or probabilities to other machines. And all this goes through this idea called shuffle. And sort is actually one thing that really stresses shuffle. And the reason is, in almost all the other categories, you start with a lot of data, and then you do some sort of filtering, you might actually shrink the data down as you go. And so the amount of data you will shuffle is actually dramatically reduced in most real data pipelines. In sorting, it's very interesting because if you want to store 100 terabyte, you pretty much have to communicate 100 terabyte across your cluster. If you want to do it reliably, you actually communicate a lot more. So in our case, sorting the 100 terabytes of data in the fault-tolerant way actually means writing and reading about 500 terabytes of I/O and then 200 terabytes of network traffic in the 23 minutes that happened. And now I'm going to go into sort of the more details about what really makes this possible. There's a lot of things we did, so I can't possibly talk about all of them. There's kernel bugs we ran into, there's file system crashes we ran into, but I'm going to focus on some of the stuff that might be relevant to the folks here. The first is, I sort of broke down the efforts into 3 different categories. The first is the rise of the cloud. So cloud is becoming increasingly popular. Everybody's building on top of it, maybe with the exception of some financial institutes. Now, EC2 has really improved substantially in the past 5 years or so. Without sort of the improvements in hardware and the virtualized resource in the EC2, this would not have been possible at all. It wouldn't have been possible for us as a tiny little startup to even get 200 machines or state-of-the-art machines. And that's becoming very easy. And also EC2 had excellent network. When we tested it, we go into it in a little bit detail later. We essentially get, there's no oversubscription on the network, so you can actually get 10 gigabyte on every single node. 10 gigabits. Gigabyte would be nice. And then the second part, the big part, is actually what we have done to Spark itself in the past about a year that actually enabled this. And the last is, it is running a benchmark. I hope none of you actually thought I would run vanilla Spark out of the box to win this benchmark. There were actually special things we actually did in order to win it. So I can't focus on all of them, so I'm going to talk a little bit briefly about the netty transport layer, because I think this is probably the one thing that's mattered to the most to people developing outside of Spark for the Scala ecosystem. And then I'll talk about the application techniques. So it turned out one of the things, as I said, that's very important of this process, Shuffle, which is really exchange of data. So it is trying to stress, in a way, the network transport layer. And in the past, we have written the network transport layer in Spark ourselves using the netty or using NIO. And NIO is great, with the exception that it's really hard to use, and there's a lot of caveats that you can get to. So one thing I did was, when I first started this effort, I tested, can I just send petabytes of data on a cluster without really sorting it? Can I just send the data across the network? And then I found, oh, we can't, because it run out of memory. There's random places where we're allocating buffers, we're not clearing them fast enough, and at the end of the day, the JVM just ran out of memory on the cluster. I couldn't even send a petabyte, not to mention sorting it. So we were looking, and then the next thing I did was, let's try to understand this network code. And then I realized a bunch of spaghetti code in Spark that was written back when we were a bunch of grad students. It was really hard to understand. And we looked at the internet. What do people use, right? Netty is actually an amazing piece of engineering. I peek into the source code of it. It's essentially doing network in a way right. It sort of implements event-driven architecture for networking, low-level networking, and then you don't have to worry about a lot of the nitty-gritty details of low-level stuff. For example, it actually recycles buffers. So instead of keep allocating different buffers, you reuse a whole pool of buffers, and then you don't have to worry about running out of memory in a way. And then it does zero copy, which means you can actually bypass. If you want to send something from a file system all the way across a NIC to another node, you don't have to read the thing into the user space buffer. It just gets sent directly from whatever on disk into the NIC buffer, and then send it across the network. And this actually substantially reduces the amount of data you have to copy and the CPU cycles you need. So it's actually fairly high performance. And then just using netty, we're actually able to push the network throughput to actually saturate about 10 gigabit links on these drifted nodes. And this is running with about 200 machines. So you can see with 200 machines, we actually get to a peak throughput of about a 220 gig here. So each node is getting about 1.1 gigabyte. And this is the two different runs, that's why it's two peaks here. And then the second part, which is probably a lot more interesting to people writing high-performance Scala code, I'll go through them later. The first is there's actually a lot of JVM Scala gotchas when you're writing high-performance code. So to start this part of the presentation, I want to give a warning. A lot of the guides here only apply to very low-level performance code. Don't blindly apply them to, it would be kind of crazy if you write all your code this way. And very often, bottlenecks might not be what you think, so try to measure before you do it. Now, which brings me to the second part, which is measurements ridiculously hard in the modern JVMs. Because I suspect about 90% of the micro benchmarks out there are actually written incorrectly in a way that's not measuring what you were hoping to. So if you really want to write any micro benchmark, look up the thing called JMH and read through all the examples in JMH, which are about 30 of them. And it tells you how to do a good benchmark. And then the other part is we actually open sourcing our internal Scala style guide at Databricks this morning. And Patrick will actually go into more details of it. Part of it has a performance section that actually goes into more details about what I'm going to talk about. So you can look it up online. And up over on Hacker News also, it's on the front page. Some of this are pretty basic actually. If you know how Scala works, it's that obvious to you. The first is actually prefer while loops. over your idiomatic Scala loop, for loop, or any other closure thing that's relevant. Very often, in pretty much any code, it's fairly often you might want to traverse an array or some list with an index. And the canonical way of doing it is just zip with index, plus a for each. And then you do sort of a partial function to lift it, get an x and I of the index. Now, this is actually fairly slow, and the reason is under the hood, there's a closure that's happening, and there's a pattern unmatching. There might be a lot of virtual function calls. There might even, in some cases, boxing, unboxing happening. So it's bad for GC, it's bad for CPU cycles, it's pretty much bad for anything performance related. It's very simple. Rewrite it to a while loop. Just do your very stupid C or Java style loop. So unlearn a little bit of functional programming, and you can get much higher performance this way, just with a loop. And don't forget this I plus equal 1, because I realize every time I write it, it goes into an infinite loop. And the second part is the Scala collection library is great, right? It gives you a lot of power. However, it's actually not the highest performance collection library out there. It is generally slower than the Java util one. But the Java util one is not that great either. There's actually a lot of high performance libraries out there. If you just Google, like for example, FastUtil, there's also a bunch of collection libraries coming from the high performance trading, the finance line that you can also find. But in general, the biggest problem with both of the libraries is they're not specialized. When you're writing high performance code, often you want to work with primitives. And if the library is not specialized, that does mean you have to box every primitive, which is actually inhibitously expensive and also very bad for GC. And then last but not least, very bad cache locality. And the other thing I'm going to mention is kind of strange. It's just private disk. How many of you know of like private disk? In about half of you, the Scala people from Scala team. So private disk. I actually learned about this after using Scala for about 2 years. And I'm like, oh, you could do private disk. So essentially what private means is really this field is accessible to all the every instance of this class A. And then what gets generated if you just do Scala C print? By the way, it's another great way of trying to understand your Scala code. When you launch, when you're trying to compile, just add a dash print. It's going to show you some sort of, I think, some internal representation, some string understanding of the code. So what happens is there's a field called a val, which is an int, and then there's an accessor called a field here, which returns, it's a function that returns an int. And then you realize in every place that actually you're calling this field, it's actually not accessing the field directly, but it's accessing the field via the accessor function. So in most cases, the JVM can actually inline it. However, we found a lot of cases that the JVM actually can't. Sometimes maybe just because you haven't run this code enough, so JIT couldn't actually inline this thing. So it becomes a virtual function call, or a dispatch every time you actually run it. But versus if you add, if you change it to private disk, what this means is only the instance, or only this specific instance of the class can actually access the field. In this case, the code that's generated is essentially just a field. And then when you have accessor, you can see it's actually doing a field access rather than a function call.
So would making accessor final also reduce the dispatch?
I think it will reduce the dispatch, but still, compare with just looking up the field. And there's a lot more stuff we talk about, so Go, but I think one of the cool things is dash print. The other one is doing micro benchmarks to actually understand it. And if you want to go, sometimes you might have to go even crazier, just looking at the disassembled assembly code. Then I'll talk about some of the other stuff we're doing in terms of sorting that's building on top. This is very application specific, but I think you can probably learn some of the ideas somewhere else. So one thing is, everybody probably understands this, garbage collection is in a nightmare. I was talking to Dennis yesterday, and he said two of his biggest enemies are garbage collection and JVM JIT. So GC is extremely hard to turn when you want to attune or then you want to stress your system. When you have over 50% of the heap full, I think it's pretty much a black magic to actually make it work robustly. both from a latency point of view and from a throughput point of view. So when we were doing the sort, there was a lot of data we're trying to stuff. We're certainly stressing the system to a fairly full memory size. So wanted to do entirely away with garbage collection, and we essentially turned to just off-heap allocation. There's different ways of doing it. The first way is if you just Google off-heap allocation for JVM, this direct byte buffer, which essentially it's very simple to use. You get a byte buffer back that's similar to your normal byte buffer, except it's off-heap. There's two limitations of this. One is it's actually only limited to the size of an int, which is 2 GB. And then the other one is very hard to recycle because it's actually only claimed by another garbage collection. If my whole point is to avoid garbage collection, why the hell am I sort of waiting for a garbage collection to happen to recycle a buffer I want? And there are ways you can actually do with reflection to recycle this buffer if you Google. However, there's actually static synchronized lock in that free for the direct byte buffer, which means if you have multiple threads running trying to recycle different things at the same time, you're pretty much going to be bottlenecked by that single lock. So the second thing we tried was actually unsafe. How many of you know of unsafe? Well, it's the same group of people that keep putting up their hands. Unsafe is this thing that you, as the name spells, it's not very safe to do. In essence, when using correctly, you could crash your JVM with a stack fault. So back to writing C. It is available as a package in most of the JVM implementations, and the reason is actually very simple. It gives you a sort of C-like memory abstraction that you can access arbitrary memory address, and you can get like a long, you can get any primitive value out of them. And so it's frequently exploited by the finance industry, who actually have the most money to pay. As a result, almost every JVM is forced to support it. Otherwise, it can't sell to that group of sort of heavy spenders. And you can't even actually create an unsafe instance directly. You have to create it through reflection. This is how unsafe it is, but trust me, it's not a lot of people use it. And in unsafe, you can actually just call allocate memory. They will give you a bunch of memory, and you can also free it by giving it back. So very similar if you're coming from CLAN. And then once you get the memory, there's actually also accessor methods that can get just help you get the primitive values out of the arbitrary memory address. So in this way, you can actually write something like the C-style essential memory access. And also Dennis here will have a talk in the afternoon that talk about how he's combining this with Scala language features to actually do a lot of things that simplify, so you don't have to write explicit get log to get from a memory address. Pretty cool project. Now, there's still a lot of caveats. For example, unsafe allocate memory at the end of the day is really just calling malloc or the system malloc. And when you're doing this at a very high frequency, you could actually bottleneck. You might be bottlenecked by the memory allocator. And a common solution of this is actually just to pull your data together. So you're still doing pulling, even on top of unsafe. And then in the case of Netty, it's actually, so the biggest part of memory allocation in this case, for small memory allocation was in the network layer, because the network need to constantly get very small packets. Whereas if I'm creating a very large buffer, like 10 GB buffer, I don't really care about how fast it is to allocate a 10 GB, because there's only so many 10 GB I can allocate. But for small buffers, it's actually very useful. You can pull them together. And in Netty, they actually implemented this thing called the JE malloc in order to sort of reduce fragmentation when you have a lot of small allocations and then pull a bunch of memory together into a pool. Just funny fact, JE malloc actually has nothing to do with the JVM, which is the guy's name. For almost about a year, I thought it was referring to something to do with the JVM. And then when you're using unsafe, you can write a lot of asserts, because just when done incorrectly, you could actually crash a JVM with a seg file. So just write a lot of assert statements, and when you're debugging, just turn the assert on. When you're not debugging and trying to win a benchmark or trying to run in production with high performance, just turn the assert off. It's very simple. Now, the other part is with unsafe, now I can access my arbitrary memory address. I have very strong control of my memory layout. So how do I sort fast, given that? So first of all, don't use the Scala library, don't use the JVM collection library, because sort there is very slow because of primitive collections. There's no primitive collections. And every time you do something, you have to dereference the object, which essentially means random memory access, which means really bad cache locality. And then the other part is with the collection libraries, when you have to do define how you compare methods, either Scala ordering or the Java comparator means it's a polymorphic virtual dispatch, which is actually fairly expensive in the JVM because it's hard to inline them. So we, in order to address that problem, we actually took the Android's team store. And the reason we took Android is different. Yes.
So is it a bug? Team store?
Yeah, it's a bug. We fixed it now. So yes. For those of you who know, Team Store is essentially now the store that's used in OpenJDK 7, Android, and Python. And lately was found a bug in some very rare circumstance that store code could actually, I think, crash. A rare out-of-bound exception. So we actually took the Team Store from Android because it has a more liberal license, and we modified it so we can actually use it to store arbitrary memory layout. So it's not based on collections anymore. And then here, be very careful with inlining. When you define more than one definition, or more than two definitions of the memory layout, you could actually destroy the inline, and it becomes horrible performance again for every time you invoke a comparator or memory layout access. What we do is we try different things. The first one is very simple. We just put the 100 byte records consecutively into a giant array or byte buffer, or not byte buffer, some off-heap array, and then we try to sort it this way. Now, the problem we run into is when we profile it, it's actually all the time we're spending doing memcopy, because every time you actually, let's imagine you're doing whatever sort you're doing, you probably do a lot of swaps. So every time you swap the record, you're swapping whole 100 bytes, and you have to do a lot of swapping in a single sort. And as a result, most of the time we're doing memcopy. It's very bounded by memory copy bandwidth. Now, the second way we take is, this is fairly, you basically have two arrays, two parallel arrays. The first array essentially is a pointer to the 100 byte record, and then you sort this one. How do you think this one will work out? Anybody? So, it is fast to swap, right? Because you only need to swap 8 byte or maybe even 4 bytes if you compress a pointer. However, comparisons become very expensive because every time, after you start sorting for a little bit, the pointers are no longer sequentially pointing to the 100 byte records in memory because there you get swapped quite often. And then every comparison now becomes a pointer dereference, which is a memory, arbitrary memory access, which actually you lose cache locality. So essentially every swap, you have a cache miss. And then now you're not swapping as much data, however, every time you compare, it's very slow. So it turned out there's actually a much better way to do this. What we have done is, for each of the record, we now store it as a 14 byte record. Whereas the first 10 bytes is just the whole key that you need to sort on. And the last 4 bytes is a pointer back to the original record. So now, what we're doing is every time you need to swap, you swap the 14 bytes. So instead of swapping 100 byte, you swap 14 bytes. And then every time you need to compare, you just need the inline for the first 10 bytes to do the comparison. You actually don't need to do the dereference at all. And this way, essentially, you get very good cache locality, and then you're also copying very little data. And as a result, we're very proud of our own accomplishments. It turned out it's a paper that published, actually, I believe the first time in, maybe even before the 95s, by Jim Gray himself, that talked about essentially this technique. They actually went a little bit further. Because for their case, they were trying to sort keys that's even much larger, so they actually only take the prefix of the key, and you only go to compare the rest of the key when the prefixes are all equal. So essentially, it's reduced the probability that you actually have to dereference. In our case, because the keys are small, they're just 10 bytes, we don't need dereference at all. We just put the whole 10 bytes in the array. And the other part, which I think would be very interesting to think about, is actually no longer about lower level optimization. It's about very high level optimization. So when we first did this Sure. So Spark is a massively parallel system. Essentially on every node, you have a lot of threads concurrently running. In this case, I have 32 threads on each node. All the 32 threads are reading from disk, doing sorting, and then writing this partially sorted result out, and then doing network exchange to finish the sort. Now, the funny thing is, when everybody's reading, everybody only gets a subset, a part of the share of the I/O bandwidth. And where everybody's actually sorting, everybody gets a subset of the cache lines. And when everybody's writing out, again, you only get a subset of your disk write bandwidth. So this is kind of annoying because essentially now all my jobs are bottlenecked in every stage by the individual resource they were competing for. So how do I solve this? It's a very simple approach. Add a semaphore. So instead of letting all the threads reading, only let a subset of threads read here. So this subset of threads will actually complete much faster than they would. And then as soon as this one completes, you let the second one, or maybe as soon as this batch completes, you let the second batch start. So now you actually have an overlap. The sorting is very CPU and cache line bound, and this one is mostly just I/O bound. You're now competing for a very different resource. And then once you actually do this pipelining, all the threads are doing different things at the same time, but eventually you actually notice they actually complete sooner than if you let them all compete for the same resource. So just to recap of what we have done, really now I'm going with a different breakdown. One is when you're trying to optimize, hyper-optimize a program, in our case, sorting, a very important thing is to optimize the single thread sorting speed. So with a single thread, how fast can you do it? And this, you have, sometimes you turn to better algorithms to do it, but a lot often, there's only really so many algorithms out there. A lot often, once you, based on the current algorithm, it is a lot about actually optimizing memory layout and optimizing the cache locality in order to get very high performance. And the second big part of it is, for pretty much any high performance program, we want to reduce the impact of the GC. And we actually took the easy way out, which is let's go around GC and manage everything ourselves. Sometimes it's not possible, sometimes it's actually possible with works like Danny's doing. I think it would be getting easier and easier for anybody to do stuff like this. And then the other part is from a high level point of view, when you look at examining resources, find out what resources are being contended, and then see if there are any ways to get around it. Sometimes it's really one line of code change that on a semaphore to reduce the bottleneck. And then last but not least, Netty actually helped quite a bit to actually have a very robust network layer. So some of you might have seen just random reports about the record. But if you want to find more about it, we have a blog post about the record itself, which also talk about some of the stuff I talked about today. And then the Databricks Scala style guide is now online. There's a performance section that we also hope to expand over time. Go check it out. And thanks. Any can take questions if there's any. Avoid unsafe.
Please sort of make us on level VLDB because we want to figure out like what's part of unsafe, are people relying on, and why, and how can we provide a functionality.
Can you approve my email? I sent an email to the OpenJDK dev, hotspot dev, but I think it's in moderator list. There's actually, so unsafe is actually not the, okay, all right, so I haven't joined the list yet. So one thing I found about unsafe is actually sometimes, I mean, JIT does a lot of smart things when you're doing like array access and all of that, but not all of those optimizations are being applied to unsafe. So sometimes actually when you use unsafe, you might become actually slower. Although more often than not, you can find ways to get around it, but it will require you to actually look at the assembly instructions that's generated from the JIT to understand what's happening. Yeah, actually,
Things are careful on that.
I skip explaining that, but we're actually doing 16 byte. Yes.
I'm curious, when you guys were looking at this unsafe path, did you also consider using native C code like using JNI, for example?
Yeah, using native JNI. Yes, actually one nice thing about unsafe is now if you want to call JNI code, you don't need to copy the memory anymore, so you can pass the pointer over. So I don't think it matters as much for this purpose to go to sort of C. As a matter of fact, the Java program might actually have inherent advantage because of a loop unrolling done by JIT. And then sometimes also like I/O and network bound. So I'm pretty sure if you write LLVM bytecode to do a sort, you could probably sort faster than this because of the SIMD instructions. But otherwise, I don't believe writing a C code would actually make it much faster than just what we're doing here. But the other part is, even though if I further improve my single node performance, at the end of the day, you probably bottleneck by the 10 gig link you can get out of the network and the 3 gig SSD throughput you could get. So it doesn't really matter anymore to optimize further for that.
What kind of performance speed up do you think you got by doing ugly things in the code versus like the pipeline and stuff?
If I remember correctly, just the semaphore alone probably speeded up by about 30 or 40%. So one line of code, or I guess 2 lines, you have to acquire and release, 2 lines of semaphore code. And the rest, although this is done after I've done all of the things above. So I would think the things above probably, if I remember correctly, going from, by the way, this is our remote memory now, it's a few months. Going from here, this one and this one, I got about the same performance. But going from this 2 to this one, I think single-threaded sorting code actually improved by about 3x. So if I remember correctly, it's taking about like 30 seconds to sort 2 or 4 gigabytes of data or something. And then doing this was less than 10 seconds.
Have you looked at implementing something like butterfly mixing to deal with the network convention? And if so, what is your take on how the company is to jump into it?
Butterfly mixing. Are you from Berkeley? So butterfly mixing is this project by this professor called John Kenny, who just proposed a new term called roofline design. And the idea is when you want to do performance optimizations, you have to look at what's the theoretical limit you can achieve, and then work towards that. If you don't get to that, you're kind of a loser in that way. Now, have I looked into butterfly mixing? So I think even before butterfly mixing, there are things we could have done. Like for example, in Spark, we actually block the network shuffle. So the network doesn't start until all the first map phase is done. It's mostly actually for fault tolerance reasons. I could have actually changed that, but in a way I would be really, it's no longer an application technique. Part of my goal was really to stress test Spark. If I change the way that works, I'm essentially just writing a custom thing that's doing this sorting. So yeah, I could probably, and then I haven't really looked into butterfly mixing on this, so I don't have any, I have no clue how well it's going to perform. All right, any, cool, I think we are done.